PPG foundation models are changing how wearable health companies build algorithms. Instead of training a separate model for every task, heart rate, blood pressure, atrial fibrillation, sleep, stress, teams can now start from a pre-trained encoder that already understands pulse wave physiology. Fine-tune for the specific task, ship faster, need less labeled data. The field moved fast between 2023 and 2025. Here are the models that matter. PaPaGei, published at ICLR 2025, is generally considered the first open foundation model built specifically for PPG. It was trained on over 57,000 hours of data from 13,500 participants across 3 public datasets: VitalDB, Mimic3, and MESA. The architecture is a ResNet CNN with a morphology-aware self-supervised objective. PaPaGei was evaluated on 20 downstream tasks across 10 datasets. Its main limitation is that the training data is mostly clinical grade, so it doesn't fully capture the noise profile of everyday wearables. That gap is exactly what Pulse-PPG addresses. Published in 2025 by researchers at Georgia Tech, Memphis, and other institutions, Pulse-PPG is the first open-source field-trained PPG foundation model. The training data comes from a 100-day study with 120 participants wearing consumer smartwatches, yielding about 55,000 hours of raw PPG collected in naturalistic conditions. Motion artifacts, poor skin contact, ambient light changes, all of it. The key finding is that field pre-training improved generalization not just to field tasks, but often to clinical tasks as well. GPT-PPG takes a completely different approach, autoregressive generation, like a language model but for pulse signals. The corpus is massive, over 200 million 30-second samples from ICU monitoring, roughly 2.2 million hours, the largest published PPG dataset. The model comes in sizes from 19 million to 1 billion parameters. GPT-PPG is heavier than CNN-based encoders and not built for a watch chip, but it proved that generative pre-training works for PPG at scale. AnyPPG introduced ECG-guided pre-training. Instead of treating PPG as a standalone signal, AnyPPG uses synchronized ECG recordings as a physiological teacher during training. The PPG encoder learns representations aligned with cardiac electrical activity, even though it only needs PPG at inference time. Trained on nearly 110,000 hours from almost 59,000 subjects, AnyPPG was evaluated across 8 downstream datasets and showed promising results in phenome-wide disease detection across hundreds of conditions. SiamQuality, published in 2024, tackled signal quality head-on. Trained on over 600,000 hours of PPG data, it uses a SimSiam-inspired framework where quality is built into the pairing strategy rather than being cleaned away. The model showed particularly strong results on respiration rate estimation and atrial fibrillation detection. Apple published a wearable model trained on data from about 141,000 Apple Watch participants over 3 years. It uses participant-aware contrastive learning, where segments from the same person serve as positive pairs. The model encodes demographics and health conditions and generalizes across PPG and ECG. The data and weights are not public, but the work likely influenced the entire field. Biot, a NEURIS 2023 paper, is not PPG-specific but important as the first cross-data biosignal transformer. It handles ECG, EEG, EMG, and PPG through unified tokenization. Moment, an ICML 2024 paper, is a general time series foundation model that includes physiological data. Both serve as important baselines. Specialized PPG models generally outperform them on pulse wave tasks. 3 newer models are worth watching. A multimodal physiological supervision model from 2025 uses ECG and respiratory signals to guide PPG pre-training, achieving up to 36% improvement in classification with fewer training subjects. A Wavelet-driven masked reconstruction model pre-trains on 17 million smartwatch segments and learns across time and frequency scales simultaneously. And PPG-Distill uses teacher-student distillation to compress foundation models for edge deployment, achieving 7x faster inference and 19x lower memory usage. What does this mean for the industry? Foundation models make it possible to treat the PPG encoder as a platform asset. New features launch with less labeled data. Personalization becomes easier. Cross-device transfer becomes more realistic. And robustness to field noise can be learned upstream instead of patched in later. The teams that can collect synchronized longitudinal, multi-context PPG at scale, paired with ECG, blood pressure, and outcome labels, will shape the next generation of wearable health AI. Clinical-grade data infrastructure is becoming a foundation model moat. 3 trends to watch. Wearable native pre-training will keep growing, multimodal physiological supervision will likely become standard, and the bottleneck will shift from pre-training to evaluation, clinical validity,